So I'm going to go over F5. There were 6 questions in this assignment. We'll go through them one at a time. Feel free to skip ahead if you are confident in how to do a particular problem. So I'm just going to go in order and you can kind of take it from there. All right, so the first one is the centripetal force at the end of a 46-meter wind turbine that is rotating at 0.3 revolutions per second. Assume the mass is 6. So 0.3 revolutions per second. So imagine here's a starting position and it has to complete this circle to do 1 revolution. That speed is 0.3 revolutions per second. So another way to think about it is 1 over 0.3 will tell you how many seconds it takes to do 1 revolution. I care about that because that can help me figure out the velocity. So in this particular case, it takes 3.33 seconds to do 1 revolution. So 0.3 revolutions per second, so 0.3, 0.6, 0.9, that's at the 3-second mark. And then finally, I need another 1/3 of a second to finish the full revolution. The radius is 46, so the circumference will be 2 pi r. So that's 2 pi times 46. And that's going to be 289 meters. So the velocity of my wind turbine is 289 meters over 3.33 seconds. And I get 86.8 meters per second. And the question is asking, what is the centripetal force acting on the wind turbine? So the centripetal force will be mass times acceleration. The sum of forces is ma. Since it's moving in a circle, we want mv squared over r. So 6 times 86.8 squared over 46. I got 983 newtons. We'll go into the assignment to check that out. 983. Number 1's correct. Moving on to 2, you have a centrifuge used for astronauts and asks at what angular velocity, so radians per second, is the centripetal acceleration. Centripetal acceleration 10g. So that's saying 98.1 because g is 9.81. If the rider is 15 meters from the center, so that's r. So it wants to know what is the angular velocity of the particular rider. Angular velocity, we didn't really talk about this in class. You won't see it on the test yet. You'll see it in a future test. But omega is your angular velocity. And v is your tangential velocity. So v over r gives you your angular velocity. So basically what we want to do is we want to find what is the velocity. We know the acceleration. And we know that since it moves in a circle, it's v squared over r. So I have 98.1 equals v squared over 15. I can solve the velocity, 98.1 by 15. Take the square root, it'd be 38.4. That's 38.4 meters per second. Now I'll go into this equation here, 38.4 meters per second over the radius of 15 meters will tell me my angular velocity. And so I get 2.56 radians per second. Remember, a radian is a measure on a circle. If this is my radius r, then a radian is a piece of the circle on the arc that is also equal to r. That's why taking the velocity and dividing it by radius tells me how many radians per second will I travel through. 1 radian in this particular circle would be 15 meters because the radius of the circle is 15. So I got 2.56. Let's make sure 2 0.56 works. And it does. That takes us to part B. And it shows a rider's cage in this particular situation. It says at what degree below the horizontal will the cage hang if the centripetal acceleration is 10 g. So they've already broken up the free body diagram for us and shown F arm Y and F arm X. It's talking about the angle below the horizontal. So that's this angle here, theta, which, because they're alternating interior angles through two parallel lines, this angle here will also be theta. So for the X direction, which is the direction of the circle, I have F arm X, which is going to be equal to mv squared over r. V squared over r is my acceleration. Now F arm X, I could also refer to that as F arm cosine theta. And my goal is to solve for theta. So this is how I got theta into my equation. You'll see we don't have mass, and that's okay. I can figure out the mass in the y direction. So this F arm y has to be what's canceling out gravity. So F arm y minus mg is 0. Or instead of F arm y, I could say F arm sine theta. And moving mg to the other side, basically solve out that F arm equals mg over the sine of theta. I'll do that substitution into here. And that'll give me mg over sine theta. Then I have the cosine theta as well. And that equals mv squared over r. All right. In order to solve this, I'll see mass will cancel out. My v squared over r, that is the acceleration. I actually never needed to put in the v squared over r because it already gave me the acceleration is 10g. So what I'm going to do is I'm actually going to replace v squared over r with 10g. That was kind of a, not necessarily a mistake, but an unnecessary step that I made earlier. This will cause the letter g to cancel out. And on the right side, I have cosine over sine, which means 1 over tangent of theta equals 10. So that means tan of theta is 1 over 10. The inverse of 1 over 10, inverse tangent of 1 over 10 tells me that theta would be 5.71 degrees. Now let's make sure that works, 5.71. And it does. Perfect. So we'll move on to 3, roller coaster. And we have this vertical loop shown. The radius of curvature is smaller at the top than on the sides, so the downward centripetal acceleration at the top will be greater than the acceleration due to gravity. This is because you got to remember the train here has 2 forces acting on it. It has gravity, mg, but it also has the normal force. It has a normal force because if you think about the point of contact between the tires and the tracks, the track is going to be pushing downwards on these tires along with gravity. Now, the question is saying, keeping the passengers pressed firmly on their seats, what speed is the roller coaster at the top of the loop if we have a given radius of 11 and the acceleration is 1.5 g? So acceleration is v squared over r. So 1.5 g. That's 1.5 times 9.81 or 14.7. So 14.7 equals v squared over 11. 14.7 times 11, take the square root, and you'll get 12.7. We'll check it out, 12.7. 12.7 works. It takes us to 4. The child on a swing. As one of the children swings on the rope, that is 8.4 meters long. Tangential speed at the bottom is 8.15. So let's think about what's happening at the bottom of the swing. On the swing itself, we have mg. That includes the swing and the child combined. And then you have tension pulling upwards. The tension will have to be bigger than mg in order for the child to swing. Because if tension was not bigger than mg, the child would not go upwards. They would not gain any vertical height. A is asking for the acceleration. And we're given a v squared of 8.15 squared. And then the radius is 8.4. 8.15 squared over 8.4 is 7.91 meters per second squared. 7.91. The next question is, what provides the centripetal force that keeps the child moving in an arc? It's going to be the tension in the rope. So gravitational acceleration, that's not even a force. The height of the tree, that's also not a force. And the weight of the child is a force, but that's actually working opposite of the circle. It's pointing outwards of the circle. 5 is a car going over a hill. In this particular scenario, you go over a hill that has a radius of 15. Mass in the car with its passengers is 1,400. The car at the highest point of that bump is given as 7.95. Determine the magnitude and N of the force exerted on the road at the highest point. So that force that's exerted at the highest point is the normal force. We would expect it to be less than the force of gravity because the car is eventually going to go downhill. So we'll say that the summation of forces equals MA. So it's normal is actually going to be negative. MG will be positive. And I know the question that often is going to get asked, why is MG positive? That's because if we think about the arc of the circle, which would be like so in this green dashed line, MG is pointing towards the middle of the circle, and normal force is pointing outwards. So now we need to solve for MG. Solve for the normal force. We have the value of everything else. So if I take this equation, move mv squared over r to the left, the normal force to the right, I would have mg minus mv squared over r equals normal. I can plug in my numbers, 1,400, 9.81 minus 1,400. The velocity is 7.95. Square that velocity. The radius of the hill is 15. And that should be enough to solve for the normal force. I punch this into the calculator. I got 7,835 for my normal force. All right, 7,835. That's forces directed upwards. So I got the first two. Part B is asking at what speed at the highest point will the car lose contact with the road? So we talked about this one in class. You're going to use the same equation, except you're going to set the normal force equal to 0. And you set the normal force equal to 0 because you've lost contact with the road. No contact with the road, no normal force. This will resolve itself to be velocity is the square root of GR. So that's the square root of 9.81 times 15. I got 12.1 meters per second. You can also take a look at the notes from day 8 of class as we go through an example just like part B. Takes us to our 6th and final problem. We have the pendulum swinging around. You are given a handful of information. Let's see. You're told the mass of the pendulum is m. You may use g, and you're also given theta. And your goal is to find what is the value of tension. So let's do a free body diagram first and foremost. So that's tension, and this is mg. The angle theta is right here. I like to use the interior angle, which would be this one here. That's 90 minus theta. It's up to you. If you do use 90 minus theta, you're going to actually have to use 2 pi because the program naturally responds to radians. To keep it simple, I'm going to use theta. So here's T. And once again, theta. So the tension force gets broken up in the x direction. It's T sine theta, also known as T cosine of 90 minus theta. And in the y direction, we have T cosine theta, which is also known as T sine of 90 minus theta. This angle here is 90 minus theta. So if I want to figure out what's the tension in the string, the y direction is going to be the most helpful because I know the most information about gravity. The y direction of this pendulum is going to be T cosine theta. That's my y component of tension. Minus mg is 0. So the tension would be mg over the cosine of theta. So we'll do mg divided by cosine of theta. If you type in the word theta, it will actually populate it for you. Part B is asking, what is the centripetal acceleration? So in order to figure out the centripetal acceleration, I will need to know information about the circular direction. In the circular direction, I have the x component of tension, so T sine theta or T cosine 90 minus theta. I'm going to use T sine theta. That will equal mv squared over r, except I'm going to back up. I'm just going to use centripetal acceleration since it actually wants AC. Tension was just solved in the previous question. It's mg over cosine theta. And I have sine theta here. The letter m cancels. Think about a swing ride at a place like Cedar Point. They don't have the riders weigh themselves before hopping on the ride. And the reason why they don't is because it doesn't matter. The mass will end up canceling out anyway. So the acceleration is going to be g tan theta. Now I mentioned before, if I had stuck with my traditional methods of doing these problems and I put in sine 90 minus theta, it would mark me incorrect because it doesn't quite understand that I'm trying to do degrees and not radians. But if I change the 90 degrees into pi over 2 radians, it goes back to working successfully. All right, now it's giving us a mass of the bob and it's giving us a length of the pendulum. That is not equal to the radius. Now they've also given us theta, and it's going to ask us a handful of things. It wants to know the acceleration, so AC. It wants to know the radius, and it wants to know the velocity. So we already know an equation for the acceleration. We just solved that in part B. So the acceleration will be 9.81 times the tangent of 18 degrees. 9.81 by tan of 18 degrees gives me 3.19 meters per second squared. To find the radius, you are told that the length of the string is 0.65 and that theta is 18 degrees. Here's the radius here. So using SOHCAHTOA, This is the hypotenuse, this is the opposite, and this is the adjacent. So that would tell me 0.65 sine of 18 would be my radius, which I got 0.2. And last but not least, what is the velocity? So the circular acceleration is v squared over r. That results in the velocity will be the square root of the acceleration times r. So the square root of 3.19 times 0.20. And I get 0.8. So let's try 3.19, 0.2, and 0.8. And it's perfect. Alrighty, well, hope you enjoyed.